Hey guys, welcome to our main lesson for chapter 3. We're going to have a decent chunk of notes here. There's another example video that is really talking about using your calculator to do a lot of these things for you. So we're not going to do a whole bunch of examples with as far as like manually calculating these. I will give you guys all those formulas so you know kind of what they are and where they come from. But we're going to use our calculator for this 99.9% of the time, unless I feel like being a real mean teacher and say do this by hand. I'm not going to do that because that's not the kind of term this is. So, first thing we're going to talk about in chapter 3 is we're talking about how to describe data, kind of our first steps into describing data, some characteristics. And there's two main characteristics we're going to talk about, and that is measures of central tendency and measures of variation or spread. Okay, so first let's talk about measures of central tendency. There are 4 different measures of central tendency. Okay, and those are mean, median, mode, and mid-range. Okay? Mean, median, mode, mid-range. Those are the 4. The most common ones that we will use in this class are going to be mean and median. Those are the 2 that we will use in the majority of any sort of quantitative study, any sort of, especially if it's continuous, but even if it's discrete data, if it's anything quantitative, some sort of a measurement, that's what we're going to use. Mode is pretty exclusively used for qualitative data, something categorical, right? Because mode is simply which category occurs the most, or has the highest frequency. There can be multiple modes, so you could have 2 different categories occur equal amount, and that's the most of all the categories, so then you'd have 2 different modes. Okay, so mode is a categorical data measure of central tendency. It's kind of a measure of kind of the most common occurrence. Mid-range is just what that sounds like. Okay, so for these 3, these are all going to be dealing with quantitative data. Okay, mid-range is simply saying, okay, what is the middle of the range of possible values? So if our values range from 19 to 30, as in the example we're going to see in the next video about chocolate chips, it ranges from 19 to 30, so then you just find the middle of that range. And that's 20, what, if I'm thinking right, 24 and a half, I believe, yeah. So that is our mid-range. So that's it. It's just literally the measure of the middle. Now the problem with mid-range is that it doesn't really tell us where the data is gathered. Right? What if everything is all at the 30, but then we have that one guy at 19? Well, now the mid-range is 24, but that's not really a measure of kind of what's going on. Okay? So, mid-range is very rarely used and not very accurate. Mode is only used with qualitative or categorical data. So now we've talked about those, let's move on and talk about mean, and then we'll talk about median next. Okay? Mean is what we typically think of when we say average. Okay, so the mean is the arithmetic average. In other words, add up all of the numbers, divide by how many numbers there are, and that is our mean. Okay? Now, there's a couple different symbols that we're going to introduce here for mean, and we're going to introduce a couple symbols when we talk about measures of spread or measures of variation. And these are very important ones. They are very similar but very, very different in what they mean and what they represent. Okay? So if you remember back to the first lesson, chapter 1, right, we said population had parameters, samples had statistics, right? Those things kind of went together. When we talk about the mean, we need to differentiate whether we're talking about the mean of the population or the mean of a sample. And so because of that, we use 2 different symbols to represent those. Okay? So x bar, so just lowercase x with a bar over the top, we call it x bar. This is the sample mean. Now the next one is a Greek letter called mu, and what it kind of looks like is a lowercase u with a tail in the front. Okay? And that's pretty much the way to write it. Okay? So that is the Greek letter mu, and this is the population mean. Okay? Both of these are found very simply. Okay, both of these are calculated. Using this formula here. Now, for those of you who have never seen this type of symbols, okay, this symbol right here is we call it it's a sigma. It's another Greek letter. But what it stands for in mathematics, it stands for to sum up. So what this is saying is we are summing up all of the x values, or the data values of our situation. Okay, so we're going to sum up all of the data values, and we're going to divide that by n. Now n, there's two types of n, and I'm going to kind of leave this here. So n So if we use a lowercase n, what that's typically representing is a sample size, whereas a capital N would represent a population size. So based on that, this right here would be our formula for x bar. And then that would make this our formula for mu. They're the exact same thing. It's just kind of the total number of data values used, right? Whether that was the total size of the sample or the size of the population. Now, we may think like, oh my God, we'll never use this because populations are huge, right? But remember, the population is simply just the entire group of what it is that you are observing, what the overall group of what you're studying. So what we are studying could be humans in general, in which case we'll never know at n because we never know the exact number of humans on Earth. But maybe our population that we're studying is simply students enrolled in this Math 243 class, in which case n is 34. I know what the population is of that class. Now I may need to take a subgroup, take a sample of that population, right? Maybe I say look at 10 people's grades. Then I'm looking at a sample. But we know what the population is. So this is a situation where sometimes, depending on what we're looking at, we know what the population size is. Okay? Now, there's a couple of really kind of important things to think about with mean when we're thinking about kind of why we use them and how we use them. And the biggest thing is that mean is really great in that it incorporates every single data value that was found within that set. Okay? Every single point is incorporated in finding this mean. So there's nothing kind of left out. No one kind of doesn't count or anything like that. Now, the downside to that is it's really susceptible to what we call outliers or extreme values, right? And if we think about income being kind of one of those things, if we think about just income amongst all of us in this class, right? Now, I'm just going to make a very oversimplification of this, idea, and definitely not absolutely correct. So let's just say all of you are students exclusively, do nothing else. That's all you do. You are a student 100% of the time. Your monthly income may be minimal, if anything, right, as a student. Whereas me as the instructor, I have a nice paycheck because being a college instructor is a good job. Think about that if you want to go into math or anything. And so my income would be an outlier. It'd be kind of higher than the majority, than kind of everyone else. It would be kind of an unusual value. And so that can greatly affect the mean of that population. So those are some things to kind of keep in mind when you're looking at trying to decide what measure of central tendency should I use for my data. So that's mean. The next one we'll talk about is the median, or this is just the middle value. Okay? And that's all it is. It's literally just the middle of our data set. Now, depending on whether our data set has an even or odd number of values, if it has an odd number of values, we will have a singular mean. We'll have one number that is our mean. If there's an even number of values, we're going to have 2. And what we do then is we just average those out, right? We find the mean of those 2 numbers. So let's look at a quick example. So I got 1, 2, 3, 4, 5, 6, 7. Not a very creative group. So that is an odd number of values. So the middle number if I have 3 here and 3 here, that means 4 is my middle number. In other words, if this is my data set, the median would be 4. Now, if I just tack on one more number, this is now an even value, an even number of data values. And there isn't a singular middle value, but there are 2 middle values. And so what we do in this case is we just go, okay, well, we just take those 2 middle values, add them together, and divide by 2. And that gives us our median for this set. Okay? So depending on which type of data set you have, that's all you do. Okay? Really nice and simple, really easy. Now, the big catch here, and this is something that's really important, this is kind of, I've cheated by making my data set the way it is. This is, so the data set must be in order. Okay? It can't just be, I can't just have my data set listed randomly 1, 8, 9, 4, 3, 9, 4, and then be like, oh, well, the middle number is 9, so the median's 9. That's not the way it works. We have to have it in an ordered manner, and then we will find the middle. And if there's repeated numbers, that's okay. We include those in that order, and it just adjusts where the middle value falls. So if we had, say, something like 1, 1, 2, 3, 3, 4, 5, 5, 5. This is our data set. This is in order. It goes from least to greatest. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different data values. So the middle one, so 1, 2, 3, 4. So our median of this set would be 3. Okay? And that's how that works. There's median. Now, one of the really nice things about median is it's not greatly affected by any outliers. Let's take this set right here, right? Our mean was 3. Let's add one more number on here. 180. Sorry, our median earlier. Sorry, our median was 3, not mean. So if I just add on one more data value, 180. Well, what does that do to our median? Well, now, since it's an even numbered list, it's going to be these two things, so we're going to average those, and 3 plus 4 is 7 divided by 2. So our median is 3.5. But our mean would drastically shift. Okay, so if you wanted to add these all up and divide by how many there are, right, do that with the original set and then do that with that added on 180, you can see kind of how greatly affected the mean it can be by a significant outlier like this. Okay. Now, one of the problems with median is it doesn't incorporate all the values. It only incorporates at most the middle 2, and that can be kind of an issue. It doesn't really give us any other ideas, but you got to kind of pick and choose your battles, right? So, if you think about what are some times you would want to use mean versus median, and if you look at the forum post, right, mode is also talked about in the forum post, it really kind of exemplifies this idea of when it's appropriate to use which one. Now, when we talk about data and its shape, it can really give us a good idea. So here are two curves. Okay, this top one here is approximately normally distributed, right? It's got kind of that bell shape with even symmetry, whereas this one down here is skewed. Which direction is it skewed? Think. That's right, it's skewed to the right. It has a longer right-hand tail. So if we look at these sets, okay, so this one here, let's say these might be some outliers out here, okay? The median of these sets, the middle value of these sets, would be about there for both of them, okay? They're at that kind of peak. However, the mean of this set is roughly the same as the median, which is great. That's one of the amazing things about normal distributions. That's why we like them so much. And later on in this term, you'll see we can take other distributions and make them normal by doing some math magic, and we will kind of work with those. However, here with this skewed to the left, it really pulls our mean over. And so our mean could be over here. Okay? So, I want you guys to think about this when you're answering the forum post for week 3. I know some people may have already answered that before this, and if you want to go back and edit or reply to yours and add anything on from this, go for it. So that is kind of how mean and median can be really representative or misrepresentative of some situations. So keep that in mind when you're working through these. Let me think. I'm just going to put this out there. I'm just going to say this. I don't want to come up with a clever way. The rounding rule. There's a question we always get asked as math teachers, and especially in stats, how many decimal places do we round to? What do we do? Unless I specifically tell you, round to this many decimal places. The general rounding rule is round 1 decimal place beyond the original data. Okay, which means if my original data is 1, 2, 3, 4, 5, I want to round to 1 decimal place. But if my original data is, say, something like 1.5, 9, 9.8, 9.7, we're going to round to 2 decimal places. Okay, so we always round 1 decimal place beyond the original data unless specifically told to do otherwise. Okay, very important. Now, let's talk about some measures of spread. Measures of spread are really important in understanding kind of how the data looks, because these are 2 normal curves that we could even say have the same mean. But this data is very different. We can see this data here is very clumped up. It's all right up in here, whereas this is very spread out. And so being able to have a measure, an idea for that measure of spread, being able to talk about that with an actual number is really important. And so just like with measures of center, or central tendency, there's a couple ways we can talk about measures of spread. One of them is to look at the range. So we talked about with measures of central tendency, the mid-range, right? So we can also talk about just the range, just kind of how spread it out is. Well, the range of numbers spans 100, right? Or the range of numbers spans 15. That tells us kind of, oh, they're really spread out, or they're not spread out very much, depending on what we're talking about. And so that is one way to do it. Again, just like mid-range, it's not really that practical. We're not going to use it a whole lot. The one that we are going to use a lot is the standard deviation. Okay? So let me write this down to get us nice and exact. Standard deviation is a measure of how much data values deviate from the mean. Okay? So standard deviation is a measurement of how much these data values in the set deviate or kind of alter, or kind of go away from the mean. Now, what this does is it takes into account every single data value in your set and how far from the mean it is. Okay? So, just like with means, we have sample mean being x bar, and we have population mean being mu. Well, here we're also going to have a population standard deviation and a sample standard deviation. It is very important that you understand the difference. Okay? A lowercase s is sample standard deviation. Now I'm going to abbreviate standard deviation, STD, DEV. Okay? And now, just like with mean, where the kind of sample was normal letters, the population was a Greek letter, same going to be true here. The Greek letter that we use to represent standard deviation, okay, is sigma. Now you're like, wait, we talked about sigma earlier, right? Uppercase, lowercase Greek letters. Sigma, that is the population standard deviation. Okay? When we look at our calculators, and if you look at the next video, you're going to see this, it's going to represent these, it's going to say S, X, and sigma X, but it's still just S and sigma. Okay? So, make sure you keep that really clear. Now, a really nice trick to help me remember is populations use Greek letters, samples use standard letters, right, or a normal Roman alphabet that we use. Okay? So if you see a letter in Greek, that is most likely meaning that it is representative of a population characteristic, not a sample characteristic. So make sure you guys keep those clear. Make sure when you guys are writing your answers for things, you're using the correct symbols, and make sure that when you guys are later in the term working with functions and things like that, you recognize what you have and what you need, and you pull the right information, especially if you pull it off the calculator. Make sure you're pulling the right thing off. Okay, now, I'm going to give you the formulas for these just so that you can be so grateful that you don't have to do this by hand. Okay? To find the sample standard deviation, there's actually two different formulas. They're the same, they're equivalent, but there's just two different ways to write it. We say that S is equal to the square root Okay. So I wrote these two down. So both of these formulas will give you the exact same value for the data set, and they'll both give us a sample standard deviation. This first one here, what we have is we have the square root of the sum of every data point minus the mean squared, and then we divide that by the sample size minus 1. This one here is saying we take the sample size, we multiply that by the sum of all of the data values squared, and then from that we subtract the sum of all the data values squared, and then we divide that by the sample size times the sample size minus 1. Yuck. Okay. To find the population standard deviation, we use a very similar equation to the sample standard deviation. The difference is what we're dividing by. Notice that with sample, we divided by the sample size minus 1. But when we deal with population, we just divide by the population size. For that reason, these two numbers will be different. So when we look at our calculators, when you look at the next video and you look at that example, those two values will be different. Now, depending on the size of our data and how kind of spread out our data, those values may be minusculely different or they may be massively different. And you have to be very careful in choosing the correct one. If you choose the incorrect one, it's going to mess up everything you do from that point on. So later on in this term, we are going to be using standard deviations a lot. And so if you don't choose the correct one for your situation, it's going to mess up every answer from that point on. So make sure you guys are very careful in understanding what S and sigma represent. Sample, population. Okay, that's enough of me bragging on about that. Now, what's really cool is we can use this to identify an unusual value, something that is kind of unusually far away from everything else. And the way we use that is very simple. The range rule of thumb is what it's called. So what the range rule of thumb basically tells us is that about 95% of data is within 2 standard deviations. And so what we can do is we can simply kind of say if something is unusual is if it's beyond 2 standard deviations away from our mean. So what's really cool is we can kind of get a minimum unusual value, and that's equal to the mean minus 2 times the standard deviation. Okay, and we can get a max unusual value, which is simply the mean plus 2 standard deviations. Okay. Anything outside of there we would say is an unusual value. That doesn't mean it's an outlier. Okay. Outliers are different. There's a little bit more kind of restrictions and circumstances that have to be checked off for that. But we can definitely say it's unusual, and we might be kind of curious as to how that data value became. Okay, that would be kind of a good idea if you're doing something with data collection and you get an unusual value. It would be a good idea to go back and check, is that value real or did I have a typo, right? If all my values are 18.6, 18.5, 18.9, 18.7, and then I've got 185, I probably just miskeyed the decimal and I meant 18.5, but we want to go back and check the data to make sure that is what we actually wanted. So, unusual values, just 2 standard deviations away from the mean. Now, one thing I want to talk about really quick, I'm just going to talk about it because it's not really used in this class. It is used in the theory behind what we do. And if you go on to take 244 and some other subsequent statistics classes, you will hear about this and you will use this. Okay? Variance is the square of the standard deviation. Okay? Variance is the square of the standard deviation. In other words, okay, the variance is equal to S squared or sigma squared, depending on whether you deal with population or a sample. That's it. That's all I'm going to talk about variance. We're done. Okay. Now, if you print it out or if you're looking at the lecture guide for this chapter, the next thing you'll see is this normal graph. I believe it looks something like this. We'll fill in some values here. What we're going to be talking about is the empirical rule. So the empirical rule is something that involves a standard distribution with its mean and standard deviation. And it's involving kind of that range rule of thumb. And what's really cool is if we kind of represent each one of these as a standard deviation. So this point here is the mean plus standard deviation. So here is the mean plus 2 standard deviations. Let me go close to my computer. Yeah, you can see that. And this one here mean plus 3. Over here, got the mean minus the standard deviation, mean minus 2, mean minus 3. Okay? Now, what's really cool with this is we can use this and we can actually figure out kind of what percentage of the data falls into each kind of piece. And the way that works is based off of 3 numbers. That within 1 standard deviation of the mean, so in other words from the mean minus 1 standard deviation up to the mean plus 1 standard deviation, there is approximately 68% of the data. Within 2 standard deviations, we get to 95%. And within 3 standard deviations, there is a total of approximately 99.7% of the data values. So, feeling old. I got my calculator so I make sure I don't mess up any numbers. What that means is if there's 68% from here to here, one of the really nice things about a normal distribution like this is that it's symmetric about the mean. So if this is symmetric, that means if there's 68% here to here, that means we have 34% in each of those. Okay. And now this is where it gets a little tricky. From here to here, we have 95% of the data. But 68 is already accounted for. So if we take 95 minus 68, we're left with 27. So that means combined in this square, in this bar, and this bar, there's about 27% of the data. Again, we're symmetric, so I can divide that up, and I get that there's 13.5% here, and 13.5% here. Okay. Now, how much is in these 2 bars total? Well, we went from 95%, then we upped it, adding those 2 bars to get to 99.7. So there's 4.7% of the data combined in here to here. Divide that by 2, 2.35. Okay. Now the only thing left is outside of 3 standard deviations. Well, if 99.7 is within 3 standard deviations, that means 0.3 is outside of it. That means this tail here and this tail here. Simply dividing by 2, we'll get 0.15% in each tail. Okay? Now, this is something that's really important. Okay? This is an idea that you need to know. Okay? So if you've been kind of skimming through these videos or whatever and jumping into the, you must learn this. You must know this. I guarantee you on your first test, I will give you problems involving this. I might even have you just fill in this whole chart. Okay? So, make sure that you know how to do this. Now, the way we use this, all right? I'm going to leave all this up, but I'm going to erase these so I can have a kind of a problem. So, let's say that for every stats class I've ever given, the test scores in the first test are approximately normally distributed with a mean of 74.3 and a standard deviation of 7.1. Okay? We could use this information, we could fill in these number values, right? We could fill these in. We know right now this one here is 74.3. And then if you subtract the standard deviation 7.1, you'd get this number here, subtract again, right? Add. So we can get those actual number values that correspond to the situation I'm talking about. So let me rephrase this, reiterate this, so that you guys can write it down if you want to. Okay? If I looked at every test, every first test I gave in Math 243, the entire time I've ever taught it, so we're dealing with population, right? That's why we use mu and sigma. If we look at that and I average out every score on every first test I've ever given in Math 243, the average, the mean, came to 74.3, and the standard deviation is 7.1. Okay? What I can do about this is I can ask you some nice, easy questions. Okay? Like, one question I can ask you is, what percentage of those test values, of those test scores, were between 67.2 and 81.4? So, what percentage of all of the test scores on the first test in my Math 243 class that I've ever given, what percentage of those scores were between 67.2 and 81.4? Now, you're like, I don't know, I don't have all that data, right? But we can use the empirical rule to make an approximation. Because we know what the mean is, and we know what the standard deviation is, we can fill in these values. And when you do, you'll see really quickly, and you might already have seen it, because it's not that hard, not that crazy jump of a number. 74.3 minus 7.1. So in other words, we're at mean minus the standard deviation. That is 67.2. So we are right here. And if I do 74.3 plus 7.1, I get 81.4. So that means I'm at mean plus 1. So what I'm asking is, what percentage of the scores fell between these values? Well, 34 and 34. So that gives us about 68% of the test values fell between 67.2 and 81.4% on the first test in Math 243. So that's the way we can use this. We have to kind of identify our points, find where they are, and then add up the corresponding values. Now, it's not always just going to be like, oh, within 1 or within 2. Sometimes it might be something like 2 below to 1 above, in which case I have to add 13.5, 34, and 34. So we have to make sure that we're kind of carefully looking at this and adding these things up appropriately. Okay? If you have any questions on this, please email me, make contact with me, and we will work it out. Okay? I'm also going to post an extra practice worksheet for this section that will have a bunch of problems for you guys to work through. Okay? I highly recommend you guys do it. It is not graded, but I will post a key. You need to do that because remember, your first test is coming up, not next week, but the week after. Okay? After chapter 4. All right? So, with that, let's move on after empirical data. What we're going to talk about now is relative standing. Okay? What relative standing is talking about is it's talking about kind of standardizing scores or data values so that they're comparable across any data set. So let me just draw 2 curves. So there's 2 standard normal curves, roughly given my artistic ability. They're on the same number line. I didn't just draw them like that because I'm lazy, didn't want to draw 2. They're on the same number line. One has a mean here, one has a mean here. Okay? Let's say this right here is 55 and this is 61. Let's say this guy right here is 58. Okay? In this data set here, 58 is a higher score, whereas in this data set here, 58 is a lower score. And we see that based on kind of, 58's above the mean here, it's below the mean here. right? If you think test scores, right? If you got below the class average, you didn't do well. If you got above the class average, you did better. So, how do I make it so that I can easily equate these? Because if I just say, oh, well, in this data set I got a score 58, in this data set I got a score 58, which one's better? It's like, well, they're both 58, but one of them is better than the other one relative to its data. And so that is why we create what we call a z-score, okay? A z-score is the number of standard deviations away from the mean a data value is. So the z-score calculates how many standard deviations away from the mean any one given data point is. Now, what's really cool about that is it also incorporates positive and negative, and in doing that, it allows us to know whether or not we are above the mean, which would mean our z-score would be positive, or if we're below the mean, our z-score would be negative. So let's write down the formula for this real quick. Okay, so I wrote down two formulas, and I wrote down two formulas because we have either samples or populations. We can see here that the equations are the exact same. It's simply our data value minus the mean divided by our standard deviation, okay? Whether that's the sample mean and sample standard deviation, or the population mean and population standard deviation, either way it's the exact same, okay? And you can see, if we look at this, right, if our data value is less than our mean, this is going to give us a negative number. Standard deviation is always positive, because remember, standard deviation was a square root. So standard deviation is always positive, okay? I didn't mention that before, I mentioned now, standard deviation is always positive. So if this becomes negative, in other words, if this x value is less than the mean, that's going to be negative, and the whole thing's going to be negative. Whereas vice versa, if our data value is greater than the mean, this is still going to be positive, and so this whole thing will be positive, okay? What's really cool about this is we get some really nice functions and some nice features with z-scores that we can build out, and we're going to talk about a lot later, and z-scores are going to come back over and over and over and over again in this term. So, So this is back to our test 1 average test scores. Mean of 74.3, standard deviation 7.1. If I have a data value that is, say, 85, let's calculate its z-score, okay? So all we do for this is we take our data value, we subtract our mean, and then we divide by the standard deviation. Okay, so grab your calculator. 85 minus 74.3, and we divide by 7.1, and I get, I'll show you on the calculator what we see. Okay, and as you can see, we get 1.507042254, and that goes on forever. How many decimal places do we go? Well, our general rounding rule was we go one more than the data. We don't know what the data was here. I mean, we can kind of make a guess because this is rounded to one spot, so then that means that this should be one more than the data, which means the data should be whole numbers. But really easy. Z-score always round to 2 decimal places. Doesn't matter what the data is. Z-scores are always rounded to 2 decimal places. So if you remember when I talked about the general rounding rule, I said unless otherwise specified, you round one more than the data. You have now been otherwise specified for z-scores. So since our z-score for this was 1.507, this is going to be 1.51. And there you have it. Okay? So, really easy, right? And the reason why we always round to 2 decimal places, there's a couple things in play. One is the fact that z-scores are kind of a standardized measurement. They doesn't reflect exactly on the data. Matter of fact, there is no units of a z-score. So if our things here are percents, right? Z-score isn't 1.51%. It's 1.51 standard deviations away from the mean every time. So it doesn't matter if our data is dealing with percents or heights or weights or whatever. All of that is stripped away when we do the z-score. And the z-scores are just this number. Okay? And so because of that, we always just go to 2 decimal places because it doesn't really matter what the original data was. We've kind of shifted to this new data of z-scores. The other reason why we do 2 decimal places is because in the olden days, by that I mean simply when I was going to school, and some teachers still teach it this way, some of the things later we'll do in the term use these tables, and those tables run z-scores out to 2 decimal places, and so we always keep z-scores out to 2 decimal places. That's kind of it. It's really easy. Okay? So, we talked about unusual values, right? We said, oh, something was unusual if it's more than 2 standard deviations away from the mean. What's really cool about that is that means, since z-scores tell us how many standard deviations away from the mean you are, a data value is unusual if its z-score is greater than 2 or less than -2, since a -2 would mean I'm 2 standard deviations below the mean. So that's really cool, right? If I know the z-score of something, I can tell right away whether it's unusual or not, just by looking at that z-score. If it's bigger than 2 or less than -2, unusual. Now, almost done. It's a long one, I know, I'm sorry. Okay. Percentiles. I hate percentiles. I don't want to talk about it. I'm just going to type it up and I'll put it on this thing. So, read the description. There's percentiles. Look it up. I don't want to deal with it. Last thing we're going to talk about. 5-number summary. 5-number summary is really easy. Again, this is something we're going to do in our calculator. If you watch the next video, it does 5-number summary for you. 5-number summary consists of, you guessed it, 5 numbers. Those 5 numbers are the minimum, Q1, median, Q3, and the max. That makes up our 5-number summary. Now, min, max, median, we've talked about all of those before. Hopefully you know what minimum is. It's just a similar minimum value. Max, maximum value, median, we talked about that. It's the middle value in an ordered list. Q1 and Q3. If you take that list, you find the median, and then take the lower half and find the median of that lower half, that is Q1. And then you take the upper half and you find the median of the upper half, that's Q3. That's it. Now, all this done on our calculator for us. Okay? What we can do with these is we can generate what we call a box plot or a box and whisker plot. And what that looks like is something like this, where we've got our minimum, our Q1, our median, our Q3, and our max. Okay? Now, these lines aren't on there, those are just arrows. What's really cool about a box and whisker plot is we can get some really quick information about it, kind of where the median is, kind of how it's split, but we can also get the general shape of the data. So for data that's skewed right, just like if we have a graph, right, it has a longer right tail. Look at a 5-number summary. It's going to have a longer right tail. So this right here, I would say, is normal. This, skewed right. And you guessed it, skewed left. Okay. We're going to talk about how to create these on our calculators so that we don't have to do this all by hand. So make sure you go and watch that next video. And that is it for you guys. Sorry this one was so long, but we got a lot of information to cover. So have fun with this, guys. Get through this section. Next week we're starting chapter 4. Chapter 4 is going to be broken into 2 weeks. Okay? Chapter 4 is really fun. It's where we start talking about kind of counting things in probability and getting into that aspect of statistics. So what does it mean for something to be a probable event, unlikely event, and things like that. We're going to get into those. We're going to get into how to do things like, what are the odds, what's the probability that you win the Powerball? How can we calculate that? It's really not that hard. We're going to do that next week. So I will see you guys then.